Thank you very much. And let me also start by first sort of thanking the organizers of this conference and also of the workshop before. I've spent 3 weeks here and it's been truly fantastic. A lot of great people came and I had lots of great discussions. I picked this topic to talk about at this conference because it's right at the intersection of sort of experiments and theory. And so I thought it would appeal to many in the audience. But maybe also it doesn't fit so well because instead of being sort of on fine structure in programmable quantum simulators, it's sort of, oh, no. Okay, it's about learning not so fine structure in not so programmable simulators using not so quantum dynamics. So kind of failing on all fronts, but hopefully there's still something you can take away from it. So I don't know if this works so well, but okay. So the setting we care about is, I want to focus about is cold atoms in optical lattices. That's something I'm sure you've all sort of heard about in the past, and it's the first analog quantum simulators we had. And so the basic setting is you take laser beams that you back reflect, you make an optical lattice, and you trap neutral atoms inside. The atoms can hop from one lattice side to the next, and they experience on-site interactions, which is this Hubbard U, which can be either repulsive or attractive. This interaction is, in many cases, it's tunable, because you have Feshbach resonances that you can tune with a magnetic field. In many of the commonly used atomic species, you can have either bosons or fermions, you can have spinful particles or spin polarized particles. And I mean, if you're not already aware of this, but there's been decades of very successful quantum simulation experiments in this platform. Because they feature lots of particles, large system sizes, and very coherent dynamics. One of the most important developments that has happened around 15 years ago is the quantum gas microscope, which was developed by several groups in parallel. And the key idea is essentially that at the end of the experiment, if you've done your simulation, you can literally make a picture of the position of all your atoms in a lattice. So it works with some very advanced lenses and some imaging technology. But for a theorist, you can think about it after you've done your experiment, you've done your some state preparation, you loaded your atoms, you've run some time evolution, you end up in the final state, rho 0. And then the quantum gas microscope records quite literally a snapshot of the atom. So it projectively measures all of the atoms in a number basis, and it gives you essentially a bit string of that either this side is occupied or this side isn't occupied. But an important question is what happens to charge off diagonal observables? This always only measures in the number basis. It's like in a quantum computer if you only measure in the computational basis. But maybe sometimes we want to measure charge off diagonal observables, and famous example, important example are currents or generalized just correlations. And I would argue that this problem is not, despite this being 15 years old, this problem is not really solved in the sense that there's no technique that experimentalists usually use to measure currents. There's a recent experimental attempt, so people care about this problem. So this is from last year, and if you, so they had a very simple protocol. It's from Monika Eidelsburger's lab in Munich, and also in collaboration with Emmanuel, who's in the audience. And the basic idea here is that you can you partition your lattice into double wells. So what you can always do is you can turn off hopping in these systems by just making the lattice really deep. And what this is doing is turning off hopping essentially across almost all bonds, except for even odd nearest neighbor in one direction. This you do by adding a modulation with a laser at double the wavelength, or double the wavelength. And then you can make these double wells where particles the only thing they can do is go back and forward. So there's very simple Hamiltonian, where you just have hopping of a particle going a bit between left and right. And then you have very simple dynamics. You just get essentially Rabi oscillations between spin imbalance and current. And if you sort of wait sort of pi over 4, like the right amount of time, then you can sort of map spin imbalance to current, and then you can measure your nearest neighbor current. Or at least you can measure the current across that bond in that double well. And that's very nice. You can also, of course, measure superpositions of these. But sort of one thing that's you notice also is that this is not so easy to generalize. Like suppose I now wanted to measure Ci dagger Cj across sort of a larger distance. It's not so, there's no obvious way you would sort of make a double well between those and then sort of make them exchange particles. So maybe we need different approaches. And of course, I mean, people have thought about these things for a long time. Oh. Maybe I'll push it back. Okay. And sort of, I mean, it's very simple, of course. I mean, you all know this. If you can only measure it in one basis, but I would like to measure an observable in a different basis, well, I just need to conjugate it with an unitary. I need to apply some unitary to my system. That sort of changes my basis, and then I can measure another observable. But in general, sort of, if you want a general basis transformation, you would need something that sort of synthesizes general unitaries, like you need to be able to implement circuits, for example. And for that, you need to work really hard. And in cold atom simulators and lattices, it's not so easy. Sometimes you also get lucky. And the sort of famous example are time of flight measurement. Like sometimes it can happen that the natural system evolution already gives you the desired unitary to transform one basis into another. And so these time of flight measurements, they would sort of map, so the momentum operator would impart onto the position operator. So if you measure the position distribution after a long time, you essentially record the momentum distribution in the initial state. That's, of course, a famous discovery of the BEC that was done in this way. But sometimes you don't want to work hard, and you're also not so lucky, and so we're looking for other ways you can do this in the specific experimental setting. And sort of something that sort of, even if you can't do very specific circuits, maybe you can do random things that are not sort of very, very specific. And sort of there's a very powerful idea. And sort of one very simple example you can think about is if I want to just measure a vector or a state, I could sort of take a basis and then measure each of the basis elements one by one. But I could also just measure along random directions. And if I take enough random vectors, they will be in general linearly independent and sort of eventually sort of span the whole vector space. And then I can also measure my vector, right? So this is sort of randomized tomography. So maybe I don't have to be so strategic and pick specific unitaries. Maybe I can just do random stuff. And people have thought about randomization a lot. I mean, these conferences like evidence of this. There's a lot of things that you can do with randomization. I'm not going to explain all of them, but because I guess you also know there's randomized benchmarking, shadow tomography. You can also get Renyi entropies from randomized measurements. I mean, many of the people who did this work are in the audience. And I guess there's a nice review article if you're interested in these sort of things. But sort of the key difference here is we can't use circuits, so we can't use sort of general sort of uniform randomness. Instead, sort of we have a very specific simulator which is very specific sort of time evolution, and we just heard earlier from Robert Huang that it's not so easy to get sort of really random unitaries from just Hamiltonian dynamics. So you have to be a little bit more creative. People have also thought about this. So how can you get randomness with limited or just global control? Sort of maybe the easiest thing you could do is you just take a fixed unitary and you wait for very long times, so up to exponentially long times, and then you get sort of a random diagonal ensemble of unitaries. So they sort of sort of similar to what Robert described, just diagonal unitary that's diagonal in the energy eigenbasis. It just has random faces. And then this will give you a tool to sort of do like some sort of randomized global tomography of your states. But sort of maybe you don't have so much time. What you can do is you can sort of add fluctuating fields to get sort of randomness faster and more local, and then you can scramble faster. Or there is also a very powerful idea, it's also been pioneered by members in the audience, is to use protected ensembles. This was sort of explained earlier also in Daniel Mark's talk, that sort of you can get a lot of randomness also very quickly by attaching an ancilla to your system and then measuring this ancilla, and you get sort of a lot of randomness, random maps onto your system quite rapidly. But sort of in general, I think in these systems, when you use sort of specific many-body time evolution and sort of generate randomness in these sort of scrambling ways, your post-processing can be, or is in general very hard, because somehow you have to keep track of the whole evolution of your system. And sort of sometimes, I mean, we are mostly interested in quantum simulation systems where we cannot keep track of the system on a classical computer, so maybe this approach is not so scalable. And so we're looking for other approaches to measure off-diagonal observables, and sort of maybe the most natural next idea you would have is to think about non-interacting quenches. So you could also do sort of time evolution in the absence of interactions, and then it's much easier to simulate and then to follow the time evolution. And sort of actually this is quite natural in core atoms. You can quite naturally turn off the interactions using the Feshbach resonance in many species. And then you get a non-interacting Hamiltonian that's essentially just a hopping Hamiltonian and a potential. And sort of this is like a bilinear Gaussian Hamiltonian. So computing the evolution under this Hamiltonian is very easy. You just take, for example, like for any operator, it's very easy to compute its evolution in the Heisenberg picture. And sort of, for example, for the covariance matrix, you can compute the evolution by, right, so just like taking the exponent of the Hamiltonian. So it's just notice, right, sort of here, this H is like this Bogoliubov Hamiltonian, so it's just n by n, it's not exponentially large. Right, and there's been some pioneering work by Marek Glusa and Jens Eisert in 2021 that showed that sort of if you do these non-interacting quenches, there's sort of numerics on a specific system, they show that you can then sort of from the experimental data you can fit the correlation matrix, and you can sort of infer correlation matrices this way. And sort of what we're looking at, what I'm sort of going to talk about next, sort of our proposal is inspired by sort of these approaches, but sort of take some sort of slightly different twists to hopefully get sort of experimentally the most easy and numerically the easiest sort of protocol. So that brings me to sort of the experimental setup we're considering. So of course we're thinking about non-interacting fermions, but you can generalize in principle to bosons without any issue. We introduce a quasi-periodic potential that comes from a lattice laser that's shown at an angle, theta. This is with a sort of a variable strength and phase. So this is sort of, we envision this sort of, you take sort of, I mean, you have your optical lattice produced by sort of back-reflected laser beams. You can always sort of take some of this this lattice beam and sort of shine it at an angle into your system. So what we think about here is that sort of this angle is fixed. So you only have to sort of put your mirrors once. You don't have to sort of keep changing them because that would be quite hard. But like it's quite easy to imagine that you could have an aperture that sort of can change the strength of this extra potential and potentially also the phase. So this requirement of a quasi-periodic potential can be relaxed to some degrees, but you need something that breaks sort of some lattice symmetries, because otherwise you won't get an informationally complete experiment. So theta is fixed, and this strength of this extra potential and its phase are variable in general, and that gives you this Hamiltonian, which is just a previous hopping Hamiltonian plus this extra potential. And then the measurement protocol, we can be very, very explicit. So the first step is you define some sort of ensemble of different unitaries that you apply. I mean, they're all Gaussian, all non-interacting. So you pick sort of a number of S different unitaries for each for each S, you first pick h, phi, and t, the time at random, and then you compute a unitary. This is, of course, easy to do. And then to do the actual experiment, you take a number of r of snapshots, your r repetitions. And for each repetition, you first sort of randomly pick one of these S unitaries that you have pre-computed. You evolve your system using this unitary, and then you record the distribution of atoms at the end. And then you just store this outcome. So both sort of this random number that you have sampled and this bit string you've gotten from your measurement. And then you have R snapshots. And then sort of this, I want to already sort of show you what you can do with this. So if we pick times between 0 and 5, so this is a unit of hopping, so it's a very short time evolution. If you take potential strengths between 0 and 5, so it's very reasonable potentials, and this sort of is kind of optional to have this random phase. And then sort of you ask for a target error of 5% for local observables. What we find is that sort of these sort of sample complexities. So you can estimate sort of, for example, you can ask, so I want to know all of the local observables in a 2x2 patch or a 3x3 patch. I think this is for 3x3 patch around some, but for any sort of 3x3 patch, sort of for all these local observables, bilinear observable in this case. Then sort of what we find is sort of for the average case in 1D, we have a sample complexity of around 2,000 shots. For the worst case, it's maybe a bit more like 3,000 in 1D. And in 2D, you have like more currents that you have to estimate, and then sort of the sample complexity increases somewhat. But I would argue it's still sort of in a quite reasonable range. I mean, I don't actually know what the actual numbers are, but sort of if you compute that sort of 1,000 samples, if you compute with 10 seconds per shots, it takes about sort of 3 hours. So this seems quite reasonable to sort of to repeat this a couple times to really sort of measure currents. There is some details on the post-processing. I can give you sort of how these results were achieved. So this is pretty standard. Like there's a lot of these sort of shadow tomography papers that sort of do very similar post-processing. So first, sort of we think about sort of this measurement map. Okay. The measurement map essentially that in our case is sort of you have this Gaussian unitary. So you evolve the covariance matrix on this Gaussian unitary, and then you take the diagonal, which is just the occupations on the sides. And then sort of this you could define for any unitary. And then sort of the vector you get out are the particle densities in the final state. And so, of course, if in a limit of infinitely many samples, we could estimate all of those densities perfectly. And then sort of this output data, which is sort of this tuple of just which of the S you have picked and whatever outcome you got, that tends to its average. And this average is just sort of some linear map applied to the covariance matrix. This is sort of your data. And sort of then what you do is you just invert this linear map. If you find an inverse to F, there's many choices, but you can make it such that the variance is minimized, so you get the optimal recovery. But sort of you can invert this. And then even if you don't do infinitely many samples, you can still apply this inverse to your data, and you get an estimator for all of these currents. And that's sort of what I showed in the previous case. You can ask then sort of what's the smallest singular value of G, or what's sort of the eigenvalue of this inverse map if I have a specific observable that I care about. And that sort of tells you sort of what is the sample complexity that I will need to estimate this observable to within that level of position. And we have to play some more games to make this local in the end. You have to truncate it a little bit and throw out some singular values. But in the end, sort of, that's roughly how it works. There was maybe a quick other question. Oh, that's annoying. Maybe if I don't know what to do. Yeah, sorry guys. So we also looked into sort of estimating the whole correlation matrix. You can also do this. But of course, now you have a lot more observables, so this makes the sample complexity worse. But you can still do it. Here we found it very convenient to borrow another idea from Wenwei and Sinwan and Daniel Mark's paper from 2023. It's this ancilla-assisted sort of idea where you take your system and let it expand into a larger space. And that sort of helps you to sort of get sort of more data or sort of more randomness quicker. And in this specific setting, we also sort of just numerically looked at how easy or hard it would be to estimate the whole correlation matrix. Now the scaling is scales, the sample complexity scales is the power law in system size in this case. And sort of it becomes, I guess, substantially worse, but maybe it's still sort of conceivable that you do maybe 10 to the 4 or 10 to the 5 shots, and then for like reasonable sized systems, you can still sort of recover the whole correlation matrix. But of course, maybe there could be some ideas of how to improve this further. I think there's a lot of data we're not using and throwing away, but at least it's possible in principle. And but of course, we can still think about improving this. You may have questions about if we can do this for bosons, and the answer is yes, we can. Whether other potentials work, we tried a little bit, and sort of generically, anything works that breaks sort of the lattice symmetries, but it might be worse or better. In principle, we also have in our papers, we give you a way also to estimate higher weight correlation functions. So like 4-point correlation functions, but of course the sample complexity gets even worse. But generally sort of all of these is polynomial in a computer science sense. So in principle it all works. But you may have a big question, sort of what happens if I'm not so sure what the potential is that I apply, or what if I'm not so sure about the Hamiltonian that I'm actually implementing, which is maybe not all that uncommon in analog simulators, especially if you apply another potential. And if you had this question, I have the answer for you. Actually, sort of we looked at the errors, and they're what you would expect. But we actually sort of in parallel also had another sort of line of research where we asked about, can we in the same setting also estimate the Hamiltonian? So again, sort of we do non-interacting quenches, and sort of now we think about a setting where you try and apply a potential. Like, for example, this quasi-periodic potential with this lattice laser, but I mean, there's been other examples of cold atom experiments in Emanuel Bloch's lab, for example, where sort of to see sort of many-body localization, you apply some sort of random potential locally. But sort of in that case, maybe because it was, the potential had to be random, so it didn't really matter you didn't have to know exactly what it was, it just had to be sort of sufficiently disordered. But in general, if we want to do high precision sort of analog simulation, we would like to know what the potentials are that we apply. And there's a big problem here is that sort of there's usually a diffraction limit, so we can't focus light as like arbitrarily precisely. And so there's always some overlap between sort of different lattice sites. I mean, it's an exponential constraint, but it exists. So we don't always know exactly what potentials we apply, or they don't. I mean, I don't, certainly. That's what I hear. But hopefully, I think, like one thing you might hope for is that your simulator is stable over time. That even if you're not sure what exactly it does the same thing each time. And then you can ask, oh, can I maybe sort of, then there's some constraint on the experimental data. It needs to be derived all from the same Hamiltonian. And so does this mean you can now sort of infer the Hamiltonian that underlies this data? So it's specifically sort of the experimental setting we're thinking about is you have a fixed unknown potential and potentially actually also unknown hopping. And that gives you sort of, again, like a bilinear Hamiltonian. But now you start from a known initial state. And for that, we take a charge density wave state because it's quite easy to prepare in practice, and it has sort of some non-trivial dynamics under hopping. So first you could come up with a provable algorithm where you where we can tell you gives you some sort of theoretical guarantees that it will work, which is you just notice that sort of the second derivative of the densities contains information about the potential differences on nearest neighbors for some sort of constant alphas and beta that depend on the initial state. And then there's an algorithm that's called robust polynomial regression that's actually been invented not too long ago. Oh, so now it works again? Okay, anyway. So then you can, with this algorithm, you can sort of robustly extract the second, like general sort of a polynomial from time series data. So you could apply this in the setting to make a time series of your local densities. They're noisy, but you use this algorithm to extract the second derivative. But the problem in this algorithm, I mean, you can prove that it works, but it requires quite high sample complexities. And sort of we tried it numerically, we tried to optimize it, but it's really quite bad. So it doesn't seem possible to use this in practice in experiments. So we thought about sort of heuristic algorithms, and sort of there's a really very simple heuristic algorithm is by just fitting the potentials by minimizing a cost function. I mean, it's really quite basic, but we tried it out and sort of it works quite well. So I still wanted to sort of still think it's worth to go through this. And sort of what you do is you just define a cost function, which is the sort of the difference of what you would predict from your current guess of what the Hamiltonian is and the experimental data you've measured. And then you optimize it. You find the best Hamiltonian that optimizes your cost function, and maybe you start with an initial guess. The caveat is, of course, that it's like a non-convex optimization problem, so you don't know if it works, but sort of we'll investigate this sort of in detail. So we just try it out, and we try to quantify the mean reconstruction error, which is just a difference. So we only look at potential differences because you can't know the absolute value of the potential. Of course, there's some sort of gauge degree of freedom, but sort of we look at the difference of the estimated potential differences and the actual potential differences in the Hamiltonian, and this is our mean reconstruction error. So then the algorithm for reconstructing potentials is the following. You start with a charge W waves, charge density wave state with some error gamma. So gamma is sort of each entry in the covariance matrix has an error gamma. We take, again, S evenly spaced points in time between 0 and some maximum time. We measure sort of then the densities at each of these points in time up to a standard deviation sigma. So for that, we need a number of snapshots per time point. That's 1 over sigma squared. Then we fit the potentials using some sort of basic sort of gradient descent optimization algorithm. And sort of in the end, you have a total sample complexity for this algorithm that's sort of S divided by sigma squared. Okay. Quite simple. Of course, you can ask how should I pick S and T max, and sort of you can just try it out. So we optimized it. So first we try to vary T max and see, okay, I mean, order 1 is enough, but sort of from this sort of here, you just look at the mean reconstruction error, you see it decreases. Eventually, sort of it grows again a little bit. And this is because we assume that you're not entirely sure what the hopping is in the Hamiltonian. But from this, you can see that, like, I don't know, any value like 5 is fine. So we also, again, pick T max equals 5. Then you can ask sort of how many time points do I need? And you see sort of at some point you get diminishing return from sampling more finely. So here important thing is we fix the total number of snapshots. So if you sample more finely in time, at each point in time you get fewer snapshots. So your data gets worse, but you get more points in time. But sort of at some point there's just this trade-off and you don't gain anything anymore. So we just pick some fixed S. And then sort of this is the main result. We sort of now ask sort of as a function of number of snapshots, how does our reconstruction error decrease? And you can see, like, I think the main takeaway of this is sort of first, it's essentially independent of system size. This is very nice because I guess the reconstruction is essentially local. The second is if we introduce errors, like for example in the green curve we added an error in the hopping, so you're not sure exactly what the hopping is. So you stop gaining from more snapshots. But it turns out so you can also fit the hopping actually, the hopping strength. So that's the red curve, and then sort of you almost recover the scaling. So this seems to work really well. And then you can sort of estimate that sort of with a total sample complexity of 10 to the 4, you get an error about 8% in all the terms of your non-interacting Hamiltonian. So that's quite nice. The last question we then answered, and then I'm done, is sort of how well can you find the optimum, right? Sort of it's non-convex optimization, so you're not sure if you can actually find the global optimum. But sort of what we asked here is you start with an error in the initial guess, I'm almost done, of size lambda. So I mean, this is again in order of hopping, so this is quite a large error in the initial guess for the potential, and it sort of keeps working until maybe 1, and then at some point it becomes harder. So this is just with one initial guess, you can still sort of optimize further, but sort of I'm just trying a very conservative stance. So even with one initial guess, you can still find the optimum in many cases. So it really seems to work. With that, I'd like to finish. My main takeaway is this is very simple and cheap and kind of really, like, it's not very complicated. And I hope this can actually find application. You can ask sort of, can you do this in the continuum? Can we maybe learn also the initial state and the Hamiltonian at the same time? Like, what's the limitation? I mean, there's some gauge degree of freedoms that you can't learn, but I mean, these non-interacting dynamics is really quite easy to use. I mean, of course, I would like to see this in experiments and maybe think a little bit about adding spins. And then I'd like to thank my collaborators, Matt Kieser and Max McGinley on the Gaussian tomography paper, and Bhavik Kumar on the sort of estimating the potentials paper. So, and thank you for your attention.
Okay, so I'd like to ask a question here. So that is, can I view this protocol as the free fermion version of shadow tomography or randomized measurements?
No, not really. No,
okay.
I mean, people have thought about match gauge, shadow tomography, and these sort of things, but sort of you need a lot more sort of controlled randomness, right? So you need to be able to sort of do a match gauge circuit, for example, to really implement shadows. Okay. And you see it in some of the things, like if we want to estimate sort of a long-range correlation function in shadow tomography, this would be as cheap as nearest neighbor correlation function, but here it really gets harder.
So I was going to ask that question. So in shadow tomography, if you address locally, then it's cheap to measure, let's say, co-local observables. But if it's a random unitary, then it's cheap for, let's say, overlaps.
Yeah,
is there any such trade-off here?
I agree. If you have local control, you're done. You don't need this, right? Sort of the assumption is you don't have local control, right? You can't do circuit. Like, of course, if you can do circuits, you have local control, individual local addressing, you're done. You can do local shadow tomography, right? Sort of this is a solved problem. But sort of we're asking sort of what if you don't have local control? Can you still actually do something?
Makes sense. Yeah. Thank you.
Yeah, thanks for the very nice talk. Maybe a trivial question, but supposedly this would also work if you want to measure pairing. I don't know if there are cases where you actually want to do it in this specific platform. But the actual maybe question is like, do you know what happens if you are actually in bosonic systems? And I guess you will have pairing, but in higher order you have also mixing between different terms. Like what happens there?
Yeah, two very good questions. So pairing is sort of AI, AJ, or like CICJ. No, so it's not a number conserving operator. So if you always measure just sort of the number, and sort of you apply these Gaussian number conserving unitaries, you will never mix with non-number conserving operators. You will never get any information about pairing. But you can, of course, you can look at a density-to-density correlation function, and sort of maybe this will, and together with sort of the local currents, this will reveal something about sort of I guess, the absolute value of the pairing.
I guess the question more is like maybe in certain system one can actually turn up that number non-conserving but Gaussian unitary, and does this still?
Oh yeah, of course, yeah. Then you could do it. I don't think this is so easy in cold atoms, but in principle, yeah. Then you could do it, for sure. Your bosonic question is if you can count the number of bosons on each lattice side, like then you can again measure the density. Or if your bosons are sufficiently dilute, then you can also infer the density. And then it's the same thing. Like, it's just measure the covariance matrix, and like it's all on the level of covariance matrices. So it is exactly the same for bosons. The question is just if you can, like, sort of measure the density on each side of bosons correctly.
Maybe just a quick comment on that. I guess depending on the system, in certain free bosons, is like number resolving measurement might be hard, but it might be easier to do things like homodynamic, where you just directly extract the variances and higher moments. So.
I agree. In principle, I agree. Homodining with sort of BECs is, I'm not sure if this has been done, but okay. You could try.
So two questions, Annie. So the distance of the correlations that you can measure, coherence, that is determined by the evolution time by some deep Robinson argument again, or?
Yes, essentially, yes.
Because you didn't say anything about that.
Yeah, exactly. So the like we have this both a local and a global scheme. So the global is where you try get all the correlations, then sort of the whole system, anything. For the local scheme, yeah, we pick a sort of like artificially a truncation patch, and sort of then you're right. Like sort of if we look at longer range, then we should go to slightly longer times. That's entirely correct. Right. We didn't sort of, so we haven't sort of really numerically looked at precisely this question of sort of how does the time scale with the range of the correlator. We either did sort of just strictly local or global. But I mean, it's not so hard to answer this question.
Maybe the second question, I mean, if we combine Richard's talk, if we could have copies, can we be more efficient?
Oh, that's a very nice question.
If I would just have two copies, can we think of protocols that are much more efficient in sampling complexity?
Yeah, you think 10 to the 4 is still too much?
No, wow. Okay, less is always better, right? So
I mean, there is
exponentially better, like Richard told us, then we would take that for sure. Yeah.
So there's one calculation I've done is if you ask sort of, I mean, I'm just estimating like a probability by getting measurement results 0 or 1, right? Sort of there's some sort of statistical limit on how well you can do this, which is just 1 over the number of like square root of shots for the standard deviation, and we're sort of a factor of 8 away from this. So you could sort of still gain something. So like we're sort of a factor of snapshots of 8 away from this for the local currents, but you can't gain more than a factor of 8 because that's impossible information theoretically, I guess.
Hi, thanks for a great talk. I was just wondering, a related question, like how you mentioned you can go to higher order correlations also. Yes. How do you? Can you just comment? How do you do it? Can you extend to arbitrary?
Yes, you can do it for arbitrary, but it's just sample complexity gets worse. But sort of the way you do it, right? Sort of in non-interacting evolution. Like an annihilation operator always evolves just into a linear combination of annihilation operator. It doesn't lead to products. So if you have 4-point correlation functions, they only mix with 4-point correlation functions. And there's like n to the 4-point correlation functions, and you always get information about sort of the diagonal ones. And in principle, you have information about the smaller correlation functions. So you apply some version of Wick's theorem to sort of decompose it into like a genuine 4-point correlation function in the smaller ones. But yeah, you need a lot more shots, I guess.
Do you need then also like density correlation to measure in first place, like higher order correlations?
Yes, yeah, exactly. Yeah, okay, exactly. You use density correlation function. That's like a 4-point correlation function you can measure. And then sort of if you apply sort of these Gaussian unitaries, you mix all other 4-point correlation functions with your density correlations, so you can recover those as well.
Estimation about the sample complexity if you do the higher order in general? How does it?
No, we should do that, but we also like both of the papers came out today. So we ran out of time. I wanted to give you an archive number to look it up, but I agree. Like this would be cool. I actually would like to hear like how experimentally realistic like even 10 to the 5 shots is, because like presumably. If you did higher order correlators, you would really need a lot of shots. So at some point it just becomes, even if theoretically possible, it just becomes unrealistic to do. Yeah.
Hi, thank you for this talk. First, maybe I will also follow up about the high order correlations. And sorry, just to confirm I understand, for the high order correlations, you kind of still reconstruct it from two-point correlations, or you have
2-point density correlations. So that's already a 4-point correlation.
Yeah, right. Yeah, exactly. But you can directly have access to that, or you kind of try to compute that based on your knowledge about this CICJ.
No. Like sort of so the density correlator you have direct access to, right? Because you get snapshots and you just sort of...
Sure. Okay. Oh, sure. That one you have direct access. I'm just saying more complex combinations of all this.
Or the other ones you don't measure directly, you infer them, right? Sort of, but that's also true for all of the other correlation functions that we do here, right? Sort of you infer them from your experiment, from your data set. You're not sort of, like for most correlation functions, you never have them sort of directly measured. You just infer them from knowing what the Hamiltonian and the time evolution is.
Can you also do non-equal time correlations?
Sorry?
Non-equal time.
Non-equal time. Essentially, yes, right? So because, I mean, non-equal depends on the time evolution, right? Sort of if the time evolution is non-interacting, then sort of you can compute any non-equal time correlation function from your covariance matrix.
Sure.
I guess.
If you that's have kind of, yeah.
I don't see like a super, like of course if it's short time, non-equal time correlation functions, you just sort of turn it into an equal time correlation function by conjugating your observables with the Hamiltonian. And that you can sort of kind of estimate, but otherwise I'm not quite sure how this would work now.
Yeah, maybe also, so for the original model of the Hamiltonian of your interest, is there interactions between particles or not at all? It's just
so
the
interactions will be present as you sort of do your experiment, but sort of like, or I don't know, like depends on the experiment you do. You do some experiment, it could have any form of interactions, right? And then you have a final state, and you want to learn something about the state.
Sure.
But then you stop having interactions. You evolve it without interactions, and then sort of you measure the state at different times. And this gives you enough information to infer properties of this final state of the experiment. But it doesn't have to be Gaussian. It can any state works.
Okay, thanks.
One more question, that is, you can measure the correlation function when the distance is a nearest neighbor, right? So can you condition on that to improve your algorithm?
Ooh,
so you use double well to measure those, and then you also use your scheme, and then conditioned on your measurement results, you might, I'm not sure whether you can improve the sample complexity or convergence.
I mean, that's a nice thought. Like there's also like, there's maybe even easier, like sort of exactly. So it would be interesting to see if you can sort of measure parts of the system and then just keep evolving the rest, or like under this non-interacting evolution. In principle, you could imagine that. It's not so easy, I guess, experimentally again, because it's not so easy to confine light to one part of your system, image the atoms without disturbing the others. So like really a lot of this talk is sort of inspired by sort of very real experimental constraints. I think sort of that's why it's not so programmable. In like really programmable systems, I think people really answered essentially all of the questions we have already sort of on how to learn stuff about, or at least measure observables. But no, I'm not sure.
Okay. All right. Are there further questions? Okay. So if not, then thank the speaker again.